The city of Austin, state capital of Texas. Historically significant, it's now in the midst of a very modern economic boom. Growing at a rate of 152 people every single day. This growth has caused some dramatic changes to the skyline. Local architect and Austinite Brett Rohde has seen his city swell before his eyes.
15 years ago, this area of Austin was largely forgotten. There were a couple of apartment complexes down here. There was some storage yards, some vacant property. It was largely not known to a lot of Austinites because there just wasn't anything going on around here.
However, this all changed in 2005 as some of Silicon Valley's biggest players decided to make Austin their second home.
The city decided, okay, let's start bringing in some real businesses, some real substantial corporations into downtown. And from that, when people started to work downtown, they decided, well, gosh, it'd be great to live downtown too.
With demand for property downtown suddenly at an all-time high, architects like Brett need to find an engineering solution to the housing crisis.
So the cost of land in downtown Austin has just skyrocketed. The more buildings we have that are coming up, the more valuable that land that's left becomes. We have really no choice but to build upward.
But building towards the sky can be a challenging undertaking. First off, you need a lot of time and builders. The Great Pyramids of Giza may have been the tallest man-made structure for over 3,500 years, but it's thought to have taken 30,000 people 2 decades to complete. Then there's finding the right piece of land. Something Italian architects got wrong in 1372, when they constructed a bell tower in the city of Pisa on soft, marshy ground. And don't forget about the weather. In the early 1300s, Lincoln Cathedral in the UK became the tallest structure in the world thanks to its lead-encased spire. But after years of rot, it collapsed in a severe storm. In Austin, architects and engineers have avoided these pitfalls and built a one-of-a-kind skyscraper. The Independent. Appearing to defy physics, its staggered projecting floors have earned it the nickname the Jenga Tower.
I think the Independent is one of the most iconic buildings that we've seen in recent history.
No one has really attempted a building this shape and this size before.
This is not something that you see in a normal tower. It's atypical. It's something that you kind of go wonder, wow, how did that get built? Or how is that standing up?
Located at the heart of downtown, the Independent stands a gigantic 209 meters tall. Mimicking the teetering, precarious wooden blocks in the game, portions of the building hang seemingly unsupported hundreds of meters in the air. Inside, there's enough space to cover over 330 tennis courts, parking for over 700 cars, and a 170,000-litre swimming pool that seemingly hangs in midair. Crowned with a stainless steel mesh, it now stands as the city's tallest structure. But this ambitious project presents some intimidating engineering challenges. How do you stop a tall, thin tower from simply falling over?
Building tall and thin brings its own challenges immediately. We have to work in a very small footprint to get everything to happen. And so that means the structure has to be incredibly efficient.
How do you create extra space over 100 meters in the air?
When you have pieces that stick out hanging off the side of the building, how do you get it there? How is that going to attach? That plays a big role in when you're 200 feet up in the air.
And stop your building from swaying in tornado speed winds.
So here in Austin, we do get high mile per hour winds, and designing a building this thin and this tall to resist those wind loads is a very big challenge.
The city of Austin has a new structure dominating its skyline. The 63-story-tall, iconic-shaped, gravity-defying, independent skyscraper. Below ground, the tower's foundations extend 35 meters into the earth. Whilst over 200 meters in the air, a specially designed crown made of stainless steel meshing tops the roof. But constructing what will be Austin's tallest building, and a feature of the skyline for generations to come, is a daunting challenge for architect Brett Rohde.
Usually on a tall building like this, you would see a standard floor plan that is used throughout from top to bottom. You sort of just repeat as needed going up, and that is a very, very efficient way to do it. Unfortunately, in that scenario, you don't get a lot of variety. I wanted the Independent to be a very interesting, striking form on the skyline. We wanted this building to touch on the idea that there's something going on here that's not completely obvious.
But creating something that breaks with tradition can be a challenge.
Some people have referred to it as a Jenga Tower. During the design of the building, I was not aware of the game Jenga. I think it's an interesting term because to me it brings this sort of idea of this sort of childlike approach to something.
But taking the design from Brett's imagination and translating it into a building over 200 meters tall is an audacious task for principal engineer Chris Swanson.
When I first saw it, I thought, wow, this is not something you see every day. This is really neat. This is really going out on the ordinary and really trying to do something that's different.
The construction process starts with the piece of land the Independent will eventually sit on. Measuring just over 1.7 acres, it massively constrains the size of the building that can be placed on top of it.
The parcel that we're allotted for this building is it's not a very large parcel.
Forcing Chris and the team to work hard to find a way to get the most floor space for their building.
The most area we could get was to create this square. So that was probably not the best shape that we could have come up with. The reason why the square shape was not good structurally was that the square shape in a skinny building created the largest projection area for wind to hit it. As anybody knows, you can get a windy day and big wind gusts. They blow stuff away. You have lawn furniture and it flies over. So those same forces hit this building, but on a much larger scale. And when they hit this building on the side that's projected against the wind, that produces a force laterally that we have to resist back down to the foundation.
To overcome these forces, Chris and his team designed the building around a central core that contains the elevator shafts, staircases, and maintenance rooms.
The building core, another way to put it, might be the central spine of the building. It's providing the primary lateral backbone resistance. The core on this building is made from cast-in-place concrete. What concrete does very well, it's an excellent material used in compression. However, it doesn't work very well in tension. Unless you have something else, it's going to lose its strength very rapidly. And that would be definitely something we do not want to see in a very tall building.
To ensure their core doesn't simply crack and fall apart, engineers must look to the pioneering innovators of the past. In the US city of Cincinnati, engineer Dan Dickrell is discovering the secrets behind a long-forgotten building that fundamentally changed the way we build tall structures.
So when you think about the history of tall buildings, Cincinnati is not exactly the first place that comes to mind. But this building right here is historic and important, just as much as those famous and iconic buildings in New York and Chicago.
Completed in 1903, the 16-story Ingalls building used old materials in a new way that was revolutionary for its time.
It's been empty for years, currently under renovation. Now, when it was built, it was the tallest concrete frame structure in the world. No one had built anything as half as tall out of concrete before because concrete itself was kind of a problem.
Although it's been used in construction for thousands of years, concrete has a fundamental flaw when it comes to building tall.
Concrete as a construction material, it's really good at resisting compressive forces. But in a building, you don't just have compressive forces, you have tensile forces too, forces that are trying to rip components of the building apart. So when concrete's under tension, it does not like it. The material will crack and break apart. And for a building of this type, that's obviously a bad outcome.
Luckily for the engineers constructing the Ingalls building, one man was working on an ingenious solution. English engineer Ernest Ransome moved to the United States in the 1870s, whereupon he patented a method for reinforcing concrete that would radically transform construction techniques worldwide.
All right, so what Ransome came up with is up here at the top of this ladder. We can see a piece of it. I'm gonna pull it down. This is rebar, so it's a steel rod that gets placed inside the concrete. The concrete and the steel work as a team. The concrete takes the compressive forces and the steel takes the tensile forces in bending and enables this magnificent structure to exist in the way that it does. Ransome's contribution to steel reinforced concrete was this fluted structure, or spiral. Now what this does is when this rebar is placed inside the concrete, it increases the adhesion or stickiness between the steel and the concrete. It's effectively the skeleton of this building where the concrete would be the body.
To find out just how much of a difference Ransome's discovery makes versus concrete alone, Dan has traveled to an advanced materials testing laboratory.
This 4-point bend test machine is going to subject these pieces of concrete just like an overhead beam would be, in terms of the top will be compressed and the bottom will be stretched or extended. The bottom region is where the maximum tensile forces are going to be, and that's where we should see cracks.
First to undergo the test is the standard concrete block.
So I'm going to slowly increase the load here. What we have here is a readout that's showing the peak load that's currently inside this concrete block. And that number is going up and up and up as this machine presses harder and harder into this block. And so right now we're at 1,500 pounds of force inside the concrete block.
That's the equivalent weight of 1.5 grand pianos.
So it's a pretty strong material in and of itself, this concrete, but at some point it's just going to have to give up. And let go. Our non-reinforced concrete broke at a peak force of just shy of 3,000 pounds. There was so much stress built up inside this concrete block that a crack formed right at the middle of the bottom surface, and it shot its way up through.
Up next, the steel reinforced concrete.
Those tensile stresses that are in there that rip the concrete apart are now basically living inside the pieces of steel, and that's the magic of steel reinforced concrete. Because when it goes, it's going to go quick. And there we go. So the test with the steel reinforced concrete The peak load was around 7,700 pounds. That was substantially larger than a non-reinforced version. So we can see the effects of putting steel inside is quite substantial and impressive.
Able to sustain more than double the load than concrete alone, Ransom's invention was a game-changing material, allowing architects and engineers to redefine what concrete was capable of.
Ransom's reinforced concrete design revolutionized the construction industry. It also proved the viability of reinforced concrete as a suitable material for tall buildings of the future. It was an ingenious solution.
At The Independent, Chris and his team have taken Ransom's reinforced concrete to new heights and constructed Austin's tallest building.
We're standing currently right now, we're inside the building core. We're actually inside one of the stair shafts inside the core. This is actually the outer wall of the building core. What I'm holding here right now is what we call steel reinforcing, or commonly termed to as rebar. This core right here is packed with a bunch of this right here. This is actually a number 18 bar, which is the largest size standard bar that you can use and commonly used in construction these days. Every piece of concrete that we have in there's going that you don't see is there's going to be pieces of rebar that run up and down the wall and then also horizontally.
In total, 206 tons of size 18 rebar helped to keep the Independent's core stiff against lateral wind forces.
We would never have been able to do what we're doing here without steel reinforcing. You really have to use them both in conjunction together. Use the concrete grate for the compressive capacity, and we use the steel rebar as we have right here to hold the tension. And when those work in unison, you have a very efficient and very durable product that you put together.
Reinforced concrete may have solved the tensile problem, but it's only part of the puzzle.
So what we're looking at here is a great view of it. This is actually the south face of the building core, the exterior face. You can see the thickness of the core. This may look big to the naked eye or the layman's eye, but for this height of a building, it's a relatively skinny, thin wall.
Building a narrow core allows Chris and the team to maximize living space in this vast tower. But it also means it no longer provides enough stiffness alone to keep the building stable.
We could have increased the thickness of this wall. That could have been a solution to do it. However, to do that, we would have probably been out to about here. We'd have probably added another maybe 6 to 8 inches, if not more, onto the thickness of this wall. And that would have just taken away from any of this free space that we have standing out here, which is much more valuable space than the concrete that we're looking at.
So how do you increase the building's stiffness without thickening the core? The solution to this problem can be found over 200 meters in the air.
We ended up integrating a use of what's called an outrigger system, as you see right here. That's these big steel trusses that you see sticking out. These are actual big structural members, and they're very integral with the lateral system of the building. These outriggers right here basically link that central backbone core, as you think of it. They link it to the outer columns of the building floor plate. So if we were to take that analogy as a skier, my body, my skinny body, that would be the core. That would be the core as we were doing. As I have my arms sticking out like this, those would be my outrigger trusses. And then the ski poles, the imaginary ski poles as we would have, those would be the columns, the outer columns, so that when I go like this, I can stay. And that's exactly what we have here. Believe it or not, outriggers are used more often, but people don't see them very often. And what's unique about the Independent that I really love is that these are exposed. It's a very efficient and effective design that'll stand here for a long, long time to come.
The Independent is the tallest residential tower in the western United States. Offset tiers extend over 5 meters from the face of the building, defying traditional skyscraper form, giving the structure its unique appearance. In Austin, Texas, a rapidly expanding population is forcing architects and engineers to reach for the sky as they attempt to build the city's tallest skyscraper. When complete, the Independent will be home for more than 360 people, with condominiums ranging in size from over 200 square meters to more than 1,000 square meters on the penthouse level 58th floor. But satisfying the demands of so many homeowners presents a problem for architect Brett Rohde.
We have so many people living here. We need to find places for everyone to gather. We need to find places for people to get out of their apartment and experience the views. We thought the best place for that sort of thing would be kind of in the midpoint of the building where people could kind of come from the taller part of the building and from the lower part of the building to meet.
Residents have been promised a raft of luxury facilities, including a gym and private movie theatre. But without enough space in the middle of the building to fit everything in, Brett and his team face a challenge.
We could have gone taller to accommodate some of those important needs of the residences, but we really felt it was much better to have everything located on one floor. We're going to need to find a way to be able to build where we need it, at what level we needed it at. Basically, we had to create space out of thin air.
So could the solution to this engineering challenge be found in the innovations of the past? In London's world-famous West End Theatre District, engineer Rhys Morgan is getting a behind-the-scenes look at one of the city's most impressive buildings.
Oh, wow, look at this. This is absolutely incredible. It's an enormous space. It really makes me want to dance and sing. It's really fabulous. You just get a sense of awe from being on the stage. It's really fantastic.
Opened in 1904, the London Coliseum remains a stunning example from the golden age of British theatre design.
When the Coliseum was built, the economy was booming and audience numbers were up. And so theatre owners and producers were really keen to cash in on this extra demand.
Entrepreneur Oswald Stoll proposed that the Coliseum be the largest and most lavish theatre in the city. However, he had a problem to overcome.
To accommodate over 2,000 people, Stoll proposed 4 tiers of seating for the audience. The problem was he'd have to put in columns or pillars to support the upper tiers. The problem with columns or pillars is that they take up valuable space for seating and they restrict the views of the customers behind.
To ensure the show could go on, Stoll turned to the leading theatre designer of the time. Frank Matcham was perhaps Britain's highest-profile theatre builder of the period. But the Coliseum presented a challenge on a scale even he'd never encountered before.
You can see here the problem that Matcham faced. The balcony floors need to be supported by these columns that I've made out of wood. Now, the weight of the floors and the people on them are transferred through the columns to the ground. The problem is, the theatre goers sitting behind the columns get a restricted view of the stage and so get a bit grumpy. And also, the columns take up valuable space that eat into Stoll's profits. But we can't just remove the columns, because this happens. I love that. So we need to find another way to support the floors and remove the columns. To overcome the problem, Matcham made use of an engineering principle known as cantilevering. Now with cantilevering, instead of using columns to support the weight of the floors, you use a steel beam inserted through the floor, and that beam connects directly to the load-bearing wall of the building. Now this floor is supported by the wall, the bottom of it is under compression, it's being forced together, whereas the top of the floor is under tension, it's being pushed out. But both the compressive and the tension forces are being pushed through the steel beam back into the supporting structure. The weight of the floor and the theatre goers is now being entirely supported by the beam and the load-bearing wall of the building. So the audience members get great views, and Stoll gets to put in more seating, increasing his profits. It's an ingenious bit of engineering, and it's this technique that Matcham used with steel and load-bearing walls to build this magnificent theatre.
Matcham's cantilevered balconies were so successful that he patented his method, allowing him to stay at the forefront of theatre design.
Wow, look at this. I'm on the balcony on the very top floor, and the view is just magnificent. From here, you can really see how incredible Matcham's design was using cantilevers. There are no columns obstructing the view for me or any of the other people on this level, nor, for that matter, the sections below and below that. I mean, it really is phenomenal. And it's still the biggest theatre in London. And that is a testament to Frank Matcham's engineering genius.
Back in Texas, the team have taken Matcham's cantilever technique and pushed it to the extreme, creating a building with vast offset tiers, which seemingly defy the laws of physics and give the Independent its definitive shape. Shane Tanner is the engineer responsible for creating space out of thin air.
So this is the level 34. This is the amenity space, where we have this large, about 30-foot cantilever that juts out from the building.
Measuring a massive 10 meters long by 27 meters wide, the cantilevered amenity truss has created a gigantic amount of additional space, housing the lounge, gym, and private cinema.
So right here is what we call an expansion joint, but this also marks the spot where the concrete structure stops and the steel structure starts. This is where the whole cantilever begins. This area over, it's completely cantilevered out. We are literally 300 feet up in the air at this location. It's completely void beneath us. There's no columns directly underneath of us on this area at all.
Ensuring that this vast piece of the building doesn't fall onto the street directly below requires 3 massive 4,500 kilo steel trusses and some precision lifting.
All right, man. Look at this, guys. This is really cool.
Once in place, the team faced the challenge of joining the trusses to the building itself.
So all these trusses connect back to the mega columns, and you can see right here the painted collar. That's a giant steel collar that's embedded into the mega column. And what we did is we interwoven steel pipes with the reinforcement to make a nice rigid connection. And each one of those collars, it's about 6,000 pounds, so they're really huge, beefy collars.
Due to the size of the cantilevered space, engineers must use 3 full-story trusses. Steel members at the top and bottom of each one attached to vertical diagonal struts that handle the compressive and tensile loads. Anchored back to the building's mega columns, they provide the floor's skeleton and structural support. Finally, they're wrapped in concrete and glass, finishing the immense cantilevered floor space.
So this cantilever portion created about 25% more square footage on this amenity level.
And by implementing a similar engineering solution on other floors, Shane and the team are able to cantilever out additional sections of the building, giving it its individual shape.
So in the condos, we use the same tension rod and compression strut system. We have one tension rod that connects back to a mega column, and then we have one compression strut that's used as a fail-safe. If someone cuts one of the tension rods, it'll transfer down to another tension rod. So all these tension rods in the condos are actually designed to hold up 3 floors, not just 1 floor.
The Independent, Austin's tallest luxury residential skyscraper. Nicknamed the Jenga Tower, its staggered, gravity-defying projections have redefined the skyline, taking the crown as the city's tallest building. But constructing a tower over 200 meters in the air isn't easy, pitting engineers against one of their biggest adversaries, the weather.
Wind conditions in Austin can range quite a bit. Luckily, on a day-to-day, the wind conditions are relatively low, and that's how it normally is for the case. However, you get those occasions on those days in a year where you have those big wind gusts. You can get gusts easily in the terms of, 60 to 80 miles an hour wind.
And occasionally, hurricanes and tornadoes can batter the city.
You can get wind gusts up to, from the 90 mile an hour, they might go up to the 300 mile an hour gusts, or even higher.
These extreme weather events not only cause chaos on the city streets, but for residents living in tall buildings like the Independent, the effect can be catastrophic.
A building moves, believe it or not. Everybody thinks they're stationary objects, that they don't move. So in a high wind event, any building that you see may move depending on the range of 1 inch to maybe 2 inches, or even farther, maybe even 6 inches.
And the higher up the building you go, the greater the amount of movement.
You may see your pictures, they may move a little bit, or you may see some rocking or something of that nature. If you spend a few $1 million on a condominium to be up in here, the last thing you're going to want to do is feel like your building is unsafe.
And it's not just the furniture Chris needs to worry about.
Where you have high winds that gusts, you don't want people to feel like they're in a boat up in the top of the building and get sick. High-rise towers, especially super high-rise towers that are skinny, such as the Independent, designing for motion is one of the biggest challenges that you have.
So could the secret to overcoming this motion problem be found in the innovations of the past? Physicist Andrew Steele has come to the Coast Laboratory at the University of Plymouth in the southwest of England to discover a pioneering piece of marine engineering.
Wow, look at this thing power up. That is just incredible. Think about the sheer weight of water those paddles are moving. This massive tank is a maritime scale model testing tank. You can put scale models of ships in here and expose them to some of the roughest conditions that they could ever experience out at sea.
In the 19th century, as the British Navy transitioned from wooden-hulled boats to iron, it was conditions like these that caused them a major problem.
This modernisation in ship design meant that they were suddenly much more susceptible to what's called rolling motion. You've got these guns, you're trying to precisely target them on an enemy vessel, but if the whole platform your gun's on is just wobbling from side to side, how on earth are you going to get a shot on target?
To demonstrate just how devastating this motion can be, Andrew is taking to the water.
So I'm just taking my boat for a walk, as you do, all aboard the HMS Orange. And what we're going to do is pop her just in the middle of the tank here. And then those huge paddles down there are going to send waves towards this thing, and we're going to see how the boat and her passengers fare. Good luck, guys. There's nothing on that ship that's going to try and stabilise it if it does get hit by a wave, so even fairly gentle waves are going to put our passengers in a great deal of peril. Okay, I think we're ready. Start the waves. I'm feeling a bit nervous for my little guys out there right now. There we go, you can see it just starts to roll about a little bit in the water. Oh, we've already had one succumb to seasickness, and two, it's not looking good for those passengers. What's crucial here isn't necessarily how big the waves are, it's how fast they arrive. And if we can get them to arrive at just the right frequency, we can start to get the boat to roll bigger and bigger, get its resonant frequency. And if we can hit that resonant frequency, then the boat's really going to start rolling, and it's curtains for those guys on board. Oh no, it's moving all over the place now. Oh, and even they've gone now. So how are we going to solve this problem?
In the 1880s, renowned naval architect Philip Watts used a Navy warship to study the effects of using water to reduce this rolling motion at sea.
As a result of Watts' study, the HMS Inflexible was fitted with a stability or anti-roll tank. And I've got a modern reimagining of one of those here. It might look like just a little Perspex box, but actually, it's a lot cleverer than that. Got a marking on the side there that I'm aiming for. That's about right. So there we go. And it's absolutely amazing to think that this could possibly make any difference. But what we're going to do is just bombard it with that same succession of waves at the same frequency. Got our passengers safely back on the ship. Amazingly, they've agreed to go again. Our tank is full of water, so let's make some waves. And here come the waves, rolling ominously out over the surface of the water. You can see the water sloshing around our tank. Oh, we've lost a little bit. Now, every time one of those waves hits it, it sloshes the water to one side of the tank. And that means that when the ship rolls back in the other direction, that water has already got momentum, which means that can counteract the roll of the ship. And it keeps the whole thing much more stable. You can see the ship is actually rolling far less than it was before, exactly as the physics would predict. Before, everyone was in the water apart from one of our sailors, but now they're all sat up, probably having quite a nice time.
The stability tank was a revolution in marine engineering.
Watts' stability tank showed that a liquid damper could stop ships from experiencing this terrible rolling motion while they're out at sea. And modern adaptations of this design are used as part of the stability systems in some of the largest ocean-going vessels in the world today.
Back in Austin, engineers have taken the design behind Watts' maritime solution and transferred it onto land. But finding out its secrets requires some legwork.
So we are up here on level 60 at the very top of the building, and we are in the room for the damper tank, and that is what we're looking at right here. This is a liquid sloshing damper. The reason that we had to use a damper tank on the top of the building, this helps keep the motion in check. We use this tank to basically slow down the motion of the building going from one end to the other. It keeps that motion in check so people don't feel seasick.
Over 9 meters wide and 3 meters high, the damper tank contains 50,000 gallons of water. Constructed from modular fiberglass sections, on the inside, vertical steel plates known as baffles help to keep the water's movement under control.
What these baffles do is the baffles prevent the water from coming back very quickly if it moves from one side to side. So if the building is moving in a direction, the water is pushed up against these vertical baffles and it holds its place over here instead of going to the other side of the tank.
But to truly appreciate the engineering brilliance behind the tank, you have to venture to a spot very few people will ever see.
Oh, wow. This is great. I've never been up here before. This is really impressive. We're standing right now on the top of the Independent, of the roof. We are, as we sit right now, we are on currently the tallest occupiable point in Austin as we sit right now. So what we're going to be looking at here, this is the hatch to basically look. We are looking inside the damper tank. We can see right here, you can see the water level and you can see some of the baffles. You see one edge of the baffle right there, and you can see it's just a piece of fiberglass. So all it is that fiberglass wall. And water is about 2 to 3 feet from the top. So I guess we are definitely doing good.
The Independent has reinvented the Austin skyline. And being part of building such a unique structure is a career-defining opportunity for the team behind it.
Over 4 years ago, working on the initial design to taking it all the way through to construction, it's literally a dream come true, and it's definitely the pinnacle of my career.
You know, I feel really proud. I live in Austin, so I see it all the time. I see it from my office. I actually see it from my house. I live with this building. This project has been really amazing, and I'm so gratified and feel so lucky to have been a part of it.
This extraordinary tower has redefined a city skyline. Its central concrete core, outriggers and 8 mega columns provide the building's strength. Enveloped in glass, the unique cantilevered tier-shift structural design provides over 360 homes and over 260 square meters of amenity space. It's a feat of engineering few thought possible.
It's constantly giving me new perspective. It's constantly giving me new hope. It's definitely been a centerpiece and enjoyment of my career. This is the reason why I became a structural engineer, to do something like this.
By looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
So when you start out designing a project like the Independent, you don't know quite where it's going to lead. We came up with something that was pretty amazing.
Engineers have constructed something radical and succeeded in making the impossible possible.
You can safely say that this building stands out. You've got the Empire State Building, you've got the Sears Tower, or you've got those other buildings in Chicago. These are iconic buildings of cities, and that's what we've created here. And when people think of Austin, they're going to know that this building is part of Austin.